Hello, everybody. Welcome back. All right, so today we are going to look at the clustering lecture, and then we are going to talk about streaming. All right. So clustering. So just a side note, next Wednesday is not a holiday, but it's the wellness day. So we are not going to have a lecture next Wednesday, but you still have the Monday lecture. Okay, so still remember what we have been discussing on Monday? We look at an algorithm called BFR, and BFR is an extension of the k-means clustering algorithm. Overall goal for BFR is to allow you doing k-means on large data set, right? So you look at the entire data set, you read a small portion into your main memory, you do some k-means or some clustering method on that small data set. Then for the data points that are close to a cluster center or are close to each other, you're going to summarize them and throw away the data point. So like this one, this is your DS. These are the data points that are close to a cluster center. And these are your CS. These are the clusters that are close to each other. Well, data points that are close to each other, but not close to a cluster center. So you summarize them, summarize them, summarize them, and you throw away the original data point. You still have the RS, which does not belong to any of the clusters and does not belong to any of the compressed set, the CS, and you will need to keep their location in your memory so that the next time when you read another chunk of your data, you can redo the clustering and see if you can assign them to a cluster or a compressed set. Okay, so that's the whole idea of BFR. In your homework assignment 5, I think your TA is going to release the assignment description anytime now. You will need to implement the k-means algorithm and the BFR from scratch. I know there are many libraries that you can use to just call the library and run the clustering algorithm, but this exercise will help you understand the difficulties in clustering. You will be able to know, okay, this really needs to run over a long iterations or many iterations, and each one is a long computation, and you will need to learn how to make it run fast. In the homework description, we also detailed the individual steps of implementing your BFR algorithm just to help you get through the assignment. Okay. And for your assignment 6, the last assignment, that will be your streaming data, which we are going to cover today and next week, next Monday. Then we're going to, well, after next week, we will have already covered all the assignment topics so you can focus on your final project. Okay, all right. So other than BFR, one more algorithm that I want to talk about is the KEWR algorithm. We're going to briefly talk about this, and I'm going to tell you what's the takeaway of this algorithm. The KEWR algorithm is also an extension of the k-means algorithm so that you can handle large data set. Well, if you remember the problem of your BFR algorithm or k-means algorithm, you always work on Euclidean space. And for BFR, you have to assume your clusters are normally distributed in each dimension. Right, so if we look at 2-dimension data set, it can be your data point can look like a circle or they can look like an ellipsis, or like this. But you cannot have ellipses at an angle, right here. Okay, so one thing that might confuse you, but I just want to make this very, very clear. Remember, each data point is one row in your table, right? If your row stores student information, the first column could be GPA, the second column could be first year salary, right? 2 dimensions, okay? And that will be something like this. And when we say normally distributed, we mean in 1 dimension, in a dimension, all the data point in that dimension is normally distributed. For example, for that student example, the student GPA is normally distributed, right? When we say normally distributed, that means we have a set of data points. If you have 10,000 students, that means this 10,000 points can be modeled as Gaussian distribution or a normal distribution, where the mean is the average of the student GPA, and you can calculate the standard deviation of your data set, this 10,000 students, so that you have this shape, right? In the Gaussian distribution, the model, the distribution is controlled by mu and sigma. So sigma is the extent, and mu is this. All right. So each dimension can have its own normal distribution or its Gaussian distribution. And when we say it can be something like this, axis aligned, that means each dimension, the variable of each dimension has a correlation of 0. Okay, so if you just do Pearson correlation, you have 0, or other correlation method, 0. Does it mean these 2 dimensions are independent? Well, maybe, because if 2 variables or 2 dimensions are independent, the correlation will be 0. However, 0 correlation doesn't mean these 2 variables are independent. Okay, these are very important. When you implement your algorithm, you will know, but I want you to know right now. All right, so the problem of BFR is it has a very strong assumption of the data set. But in reality, when you look at your data set, it's very often they are very noisy and they could have a shape like this, right? So it's not an ellipsis anymore. And even you cannot really talk about axis aligned because the shape looks like this. And that's how your QR algorithm would be able to handle. Okay, so at the same time, your QR algorithm also assumes a Euclidean space. So Euclidean distance for your data set, this is the same for your k-means algorithm. It allows your clusters to have any shape. So the difference between the QR and the BFR is for summarizing a cluster, like a DS set or compression set, your BFR, because of the normal distribution assumption, you can use sum and sum square and n to help you summarize a cluster. But because of QR do not have those strong assumption of the data set, all these metrics, all these vectors in that n number does not make any sense, right? Because we don't assume a normal distribution, you don't need them. In QR, they are going to use a collection of representative points from each cluster to represent a cluster. And we're going to look at what does this mean. So the QR algorithm is also a 2-pass algorithm. For the first pass, you pick a random sample of points that would fit into your main memory. You do an initial clustering. You can do hierarchical clustering, and you group nearby points and clusters, right? We covered hierarchical clustering before. Then for each cluster, because now you want to throw away some point and read in a second chunk of your data, right? So how do you throw away points? You want to throw away the points that are already clustered into some cluster formation. To do this, you are going to pick representative points for each cluster. So for each cluster, you pick a sample of points as dispersed as possible. So a sample, this can be 4 points, 5 points, 10 points, 200 points. It all depends on your memory requirement. Right? So if you only have a few clusters and you have huge memory space that you can use, you can pick more samples. And you want them to be as dispersed as possible because a cluster look like this. And let's say these are the data points. So to pick samples that would be able to help you describe this cluster, you want to pick maybe one here, another one here, another one here, 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 and here, right? So somehow give you the location and the shape of that cluster. From the samples, we are going to move the samples, say 20% toward the centroid of the cluster. So this will give us a more compact cluster formation, right? Remember, our goal is to have compact cluster, and if you move them toward the center, that will help you to reduce the probability to have some empty areas here, right? Think about this. Let's say this is your cluster, and if you just pick points at the boundary, you might have a cluster look like this. Very dense on the left side, but very sparse on the right side, right? But you actually want to represent this dense part. And we assume that if you are close to the centroid of the cluster, it should be dense. So we're going to move all the samples 20% toward the centroid of the cluster. You can move more. All right, so the initial cluster might look like this. So 2-dimension in this case, you have age, you have salary, you have initial cluster, one cluster, another cluster, another cluster. So once you finish this clustering step, what's the next step? Before you can read in another chunk of your data, anybody? No one?
Pick some of the points.
Pick some of the points, yes. Great, thank you, Luke. So let's say we pick all these points, right, as dispersed as possible. Then you can throw away the other data points and use all these selected samples to represent your clusters. So say you pick 4 points for each cluster, 1, 2, 3, 4. Then you move them close to the center. And this is your information about this cluster. And you do this for every clusters. Now in the second pass, you are going to rescan the entire data set, visit each point in the data set, and place a data point to the closest cluster, right? So if you have a point here, we go back to the previous slides. If now you have a point here, you can compare this point to all these 4 samples here and the 4 samples here and here, right? There's multiple ways you can do this to compare their distance, and we are going to show you. So you compare them and place that point or assign the point to the nearby cluster. And this can be your normal definition of closest. It could be find the closest representative to P and assign it to the representatives cluster, or you can use the centroid of each cluster by computing the centroid of the sample and measure the distance from the centroid to your point. Then you do the assignment, you rearrange your cluster, pick the samples, remove all the data point, except the samples, and then you read in another data set. That's it. So pretty simple approach. If we compare CURE with BFR, we know that your BFR the data set should be normally distributed in each dimension. For Cure, it does not assume any particular distribution of your data. For the representation of clusters, remember in BFR, we are using centroid, right? Because you have this sum vector and you have this number n. You can use sum vector divided by n to calculate the centroid. In Cure, we are using a set of representatives because your cluster can be in arbitrary shapes. Both of them assume the data is in the Euclidean space, so you can calculate your distance measurement using Euclidean distance. So last thing I want to talk about, which is pretty important in clustering, is standardization and normalization. So for example, let's look at our student example. You have student GPA, you have student salary. Okay, and these are all the data points. Before you do any clustering or any machine learning work, one of the very important pre-processing step is either standardization or normalization of your data. So why is this important? So think about this. If you want to calculate the Euclidean distance between two data points, what would be the maximum distance between two GPAs, assuming your GPA is 0 to 4? That will be 4, right? If you only look at the GPA dimension, the maximum distance is 4. What about the salary dimension? What would be the maximum distance? Well, that would be from the minimum salary 0. Well, if you do volunteer work, that's probably a minus number, right? Minus 10,000 for a year. And the maximum could be, I think right now our master students are running something like 280K per year, right? Fresh graduate. And your distance between this is huge. This is 290K. So if you're using Euclidean distance to calculate the distance between two data points, that their distance in the GPA doesn't really matter much because this component, the second component, varies a lot and the range is huge. So that's why people will do standardization or normalization before they do any clustering. So for example, normalization will take minimum value and maximum value. So you just take an x in this dimension, subtract it by the minimum x, and divide it by the maximum x, right? Or you can say, I want to subtract by the average. And what would that give you? Well, that will give you 0 means you are at average, plus number, that means you are more than average, right? But usually you just subtract mean divided by maximum, it will give you a scale of 0 to 1, right? Put your data point within 0 and 1. And this way, your two columns or two dimensions has the same scale and your Euclidean distance will work. So this is normalization. Standardization is doing similar things as well, but when you normalize it, one extra step for standardization is you want to divide your data set with the standard deviation in this column. Okay, so that's very similar to what we have been talking about in, let me find it here, your Mahalanobis distance, right? You're dividing this sigma, the standard deviation on each dimension. So what does this give you? Well, this gives you this. If you divide it by the standard deviation, that means you take into account the variation in each dimension so that your distance measurement becomes very similar to this, not this. Okay, so that's standardization. So if you are still not sure, you can just Google standardization versus normalization and look at some examples. It will be a good exercise. So when do you do standardization? When do you do normalization? Well, very often, well, the real answer is you still want to try both and test it on your data set for your specific application. But there are some general guidelines. If the 2 columns or 2 dimensions has incomparable units, like age or versus GPA, or like in our case, GPA and salary, you want to do standardization because you want to remove the variation from your data set, your dimensions. If the 2 columns or 2 dimensions are using the same unit, but having irrelevant features, for example, one column is the commuting miles, the other columns is maximum jogging miles, right? The units are the same, but these 2 columns or 2 features are irrelevant. Then you do standardization as well, okay? The same concept. If they are using the same unit and similar features like air quality values today versus tomorrow, or the length of right arms and left arms, you would just do a normalization. Okay, so keep in mind, in this case, standardization is often the way to go, but sometimes you do normalization. All right, that's everything I want to tell you about clustering. Any questions before we move on to streaming? You can find your streaming slides on Piazza. All right, mining data streams. So mining data streams is an extremely interesting and popular topic these days. Because I think one thing is because the devices are getting really cheap and you can install sensors everywhere, and all the sensors is transmitting data to some location, and there's a need to analyze all this data, this streaming data, in real time, right? So for example, you're going to see a few examples. And all the algorithms that we are going to talk about today, wait, let me do one thing. Okay, cool. So almost all the algorithms that we are going to talk about for this topic is extremely simple and confusing at the same time. Simple means the way you need to calculate, the things that you have to calculate, or the algorithm itself, it's very easy. However, as to how does the algorithm work and why this works is not easy. So just bear with me, and if you have any questions, feel free to answer. But sorry, feel free to ask me in the chat. All right, the roadmap. So we're going to talk about the motivation. I'm going to talk about a few cases for streaming, and then we're going through sampling, filtering, counting, and sliding windows. Some of the most commonly used stream data analysis method. All right, data streams and applications. Queries can be streams, right? So if you build an API, for example, build an API for Google or build an API for your own organization, you want to be able to understand how other people use your API, right? And every time when they send a request to your API, that's streaming data. Say if you have 1 million users at the same time, you're getting 1 million queries per second. And you often want to ask questions like how many unique users at Google last month, or how many unique users has queried Google in the last 2 minutes, right? And that you have to take into account your real-time data stream. Or URL streams while you're crawling. So for example, when you send out the crawler to read web pages, parse the page, and get the URL in the page in each page back, storing it in a database. It's streaming data, right? All these crawlers are sending data back in real time, and every data tuple represents some information of some HTML and some URLs. So a common question people might want to ask is which URLs have been crawled before? So how do you answer this very quickly? Sensor data, say you have a temperature sensor or weather station. You want to ask what's the maximum temperature so far, or what's the maximum temperature today, right? So these are queries on streaming data. For streaming data processing, we assume that the stream of your tuples will be your data points, arriving at a really rapid rate. So in contrast to the traditional database management system, where you can store all your data points or tuples in a static place or secondary story, and when you query, you have the full picture of the entire data set, right? And for streaming data, it's infeasible to use all tuples to answer queries. One reason is you usually cannot afford to store all data points in main memory, right? If you want to use all data set or tuples to answer queries, say all data points in the last 10 years, that'll take a lot of time to read them from the disk, put them in memory, and run the queries, return the result. And very often you want to have a real-time answer, and you cannot do this. So too much computation. And one thing that's critical is query response time. Streaming data or streaming analysis very often require a really quick response time for your queries. So there are two types of streaming data queries. The first one is standing query. So standing query will be executed whenever a new data point arrives. So it's keep running this query over and over. You usually would just keep only one value, only one answer, because when a new data point comes in, you throw away the old answer. For example, report each new maximum value ever seen so far in the data stream, right? That's a standing query. Because every time, say temperature, every time when you receive a new temperature, you compare that with the old maximum temperature. If the new temperature is higher than the old maximum temperature, you use that to replace the maximum temperature and throw away the old maximum temperature, right? You always keep one values. Ad hoc queries. These are just our normal queries asked one time. You don't rerun it every time when a new data point comes in, but this needs the entire data stream to have an exact answer. That means to be able to answer this type of queries, you are usually looking at a window of the data stream, say 1 month. For example, what is an example of the ad hoc queries is what is the number of unique visitors in the last 2 months, right? So this require you to require the machine to look at the streaming data in the last 2 months and to be able to come up with the unique number of visitors in this 2-month data set. If we look at stream processing models, here are your data stream. This is your current time. These are the past time. This is your query stream processor. When the data stream comes in, the standing query is running here every time it will generate an output. Ad hoc queries will ask the processor to do something, and the processor also has its own memory space to store some windows of the streaming data so that it will be able to answer these ad hoc queries. Also, the stream processor, the stream processing processor, has some way to store the entire data stream into archival storage, right? This could be a relational database. And some limited working storage that can store temporary data for answering ad hoc queries or standing queries. Remember when we were showing, oh, I don't think I ever show you guys our architecture, our system architecture for traffic data set in Los Angeles. So we have a system that's collecting traffic data, real-time traffic data from LA Metro. And we have been doing this for 11 years. And there's thousands of sensors, and you know that we cannot store thousands of sensors for 11 years of data in the main memory. Right, so we have a relational database, we have a distributed file system to store archive data. So those are data older than 1 month or maybe 6 months. I don't remember exactly. But for more recent data, we store it in memory database. And we also have some memory space to handle even more recent data, like in a day, to handle different types of string queries and to help machine learning models to train and test. For example, let's say you have a machine learning model that is used to forecasting for the traffic for the next 6 hours, okay? And the input for the machine learning model is the traffic speed at each sensor in the past 12 hours. That would be your standing query, right? Every time when you are having a new speed information, you collect 12 hours, you send it to the machine learning model, and it will generate an output. And the new forecasting result is going to replace the old forecasting result, and you keep doing this when a new data set comes in, okay? So 2 methods or 2 models for stream processing. So one example of stream query is running average. This is a very common operation that people want to do on streaming data. So say given a window size of n, we want to report the average values in this window n, whenever a new value comes in. So the n can be 1 hour, and the value could be temperature, right? So we want to report the average temperature in the last hour when a new temperature value comes in. And somehow n is too large, and we cannot store the entire window, this past hour's temperature, in the memory, right? Let's say you have 1 million sensors all over the world. So how do you do this? So to do this, you can take first an input, you accumulate the sum, their sum, and count. Right, once you have the sum and you have the count, you can easily calculate the average. That will be sum divided by count. When you have a new element comes in, instead of storing the entire n input, now you just store sum and count and the oldest value in this window n. When you look at a new value I, you are going to change your average by adding this to the average. Right, so what is this? Well, I is the new element, new temperature, latest temperature. J is the oldest temperature in your window, right? You just need to compute their difference, and because you want to calculate average, you need to divide it by n, and you add this number to your old average value, then you're done. And this is because the window size is fixed, so you just need to discard this oldest value J, and you will be able to come up with your answer, right? This one is still very easy, running averages. When you have a new value, you throw away the old value. But think about this, what are the values you have to store? Well, you need to know your window size n, right? This has to be in your memory. For the first time you calculate the average, you have to store sum, you have to store count. But after the first time, after the first n values, you can throw the sum and count away. You can just store the average value and the oldest element. So 2 values. And because you know the window size, well, you may need to store this n, right? 3 values, average, n, and the oldest element in this window. Then you will be able to process lots of data streams to calculate running averages at the same time in memory. So pretty cool. All right. So first one, all the algorithms I will be talking about are here. The first algorithm that we're going to talk about is sampling. So we look at this problem of sampling many times in this class, right? So sampling from data stream, why is this different? Let's look at one example. So say the scenario here is a search engine query stream. This is your streaming data. And this stream has tuples, and each tuple contains user, query, and time. So this is one data point. You just think of a tuple is a data point. It's just coming in at a really fast rate. And we want to be able to look at all these tuples in real time and answer questions such as how often did a user run the same query in a single day, right? This will be important for a search engine. And we have some constraints. The constraint is that we only have the memory space to store 1/10 of the query stream, okay? So we want to process a single day's query, but we cannot store the single day query because that's too large. We can only store 1/10 of the query. So we have two methods. The first method is sampling your data stream at a fixed portion. The second method is to maintain a fixed size sample. So we're going to talk about this first. So how do you do sampling? Anybody? Remember in our prior lecture, we are reading all these baskets, right? And we have the sampling methods. We say, let's say you only want to sample 50% of your data. How do you do it? Are you going to read the first 50% and you're done? Or do you have other method to do this? Well, Sun algorithm, so Jun says Sun. Sun algorithm is for finding frequent item set. Now I'm talking about sampling strategy. So our last sampling strategy is like this. When we read a basket, we are going to throw a dice. We say, all right, the dice can only have values of 0 or 1. Since we only want to sample 50%. If the dice has 0, we are going to throw away this basket. If the dice shows 1, we are going to retain this basket in the sample, right? Pretty easy. Every basket, you throw a dice or you generate a random number. So can we do that for data streams? For search engine query streams, you have streams of tuples. You can think of this as a data point or a basket, right? Each one has this information. And the example query is what fraction of queries by a user are duplicates. Right? We want to know duplicates, fractions of duplicates. Our assumption is we do have the space to store some tuples for the calculation, but we can only store 1/10 of the stream tuples, right? And we are looking at a day's worth of queries. So naive solution, usually naive solution doesn't work. Naive solution for each tuple, we're going to generate a random number from 0 to 9, right? Like our throwing a dice, our throwing a coin example. And after we generate a random number, if the random number has 0, we're going to store the tuple into our sample, right? Because now you're going to take 1/10 of the sample, you only care about 0. And what would be the sample rate? Well, the sample rate will be 1/10. Great, right? For the tuples. So example streaming tuples, you have John query data mining and timestamp, Mary queries ANF 553 timestamp and so on. But what would be the problems? Is this sampling strategy can help us answer that question of duplicated queries? Well, no. But why? Let's look at one example. Say the true fraction of queries with duplicates. Let's look at if we have offline data set. If we have all the data set, we can store all of them. And how do we calculate the fraction of queries with duplicates. Let's say a user issued S queries once and D queries twice. Okay, so this is saying this S type of queries and D types of queries. If you look at here, the user queries data mining once, INFF553 once, movie twice, Tom twice. So Tom and movie are D types of queries, data mining and INF553 is your S type of queries. Okay, so very important. This is just terminology. So the total number of queries and duplicates is S plus 2D. Why do we have 2D here? Well, because this 2D queries appears twice, right? So movie is a D query, Tom is a D query. So appear twice, the total number of queries is S appear once plus D appears twice, so 2D. The true fraction of queries that have duplicates is D divided by S plus D, right? If you only look at unique queries, this is the number of unique queries. This is the number of unique queries that has duplicates in your data stream, right? And we want the sample rate of 1/10. So let's look at the example. So queries with duplicates in the sample. Let's say the sample contains S/10 and 2D/10. Okay, so S/10 is our S type of queries such as data mining. 2D/10 is our D queries such as movie or Tom and Tom. So if your sample is data mining, movie, Tom and Tom, what would be the expected number of your D queries with duplicates in the sample? So let's look at the sample. What would be our D queries? Well, your movie is a D query, right? Because it has a duplicate in the original data stream. Your Tom is a D query because it has a duplicate in the original data stream. You also have another Tom, so you have three scenarios: S, D, D, and D. So you can have things like movie. Movie is a D query in your original data, but it does not have duplicates in the sample, right? Because you are sampling each data point with 1/10 chance of choosing it. So it could be that you only pick one movie and you discard the other one. Also, it's also likely that you are going to pick both of the query keywords Tom and Tom. This will be the D queries with duplicates in the sample. So for example, both Toms appear in the sample. So this way, in your sample, you're going to have S type of queries. You're going to have D queries that do not have a duplicate in the sample. You're going to have D queries that do have a duplicate in the sample. Okay. So let's look at queries with duplicates in the sample. Say this is your data set. You have S equal to 800, D equal to 100. So the entire stream has 1,000 queries, right? Because every D types of query has 2 words. Are we good so far? S type of query has 1 word. D types of query, every type, like movie, would have 2 movies. Tom, where you will have 2 Toms. So you need to add another 100. This is the total number of queries. Say each DJ has the probability of 1/10 to be selected into the sample. So the probability of 2 DJs being selected into the sample is 1/10 times 1/10. Right, so this means you have 1/10 chance to select the first Tom and 1/10 chance to select the second Tom. Okay, so and there are D numbers of D queries. So the expected numbers of pairs, this type of d-queries in the sample is d times this probability, so it's d over 100. Let's say now we are going to look at the d-queries without duplicates in the sample, like movie. Again, the sample contains S queries and your D queries. So what's the expected number of D queries without duplicates in the sample, like our movie example? If we look at our queries here, the expected number of D queries that only one of the two words got selected into the sample is, say the first one got selected but the second one was not selected, right? So selected 1 over 10, not selected 9 over 10. Complementary probability. Or you can have the first one not selected, 9 over 10. The second one is selected, 1 over 10. So you have two types of scenarios, the same probability, and it will be 9 over 100 times D, because you have D duplicates queries, plus the second scenario here. All right, first scenario and second scenario. And this is the expected number of duplicate queries that do not have a pair, or only one of them is selected in the sample. So let's look at our sample. If we are going to use our sample to help us answer this question, the question is the fraction of queries in the sample without duplicates. So D over 100 divided by S over 10, right? You have S single queries over 10. This is your sample rate. You have D over 100. This means the duplicates, and the duplicate queries, the queries where both words got selected into the sample. This is the expected number of the D types of queries that only has one word selected into the sample. This is movie. And this is TomTom. So if we're going to use the sample to calculate the answer for this, it's here. And it becomes D over 10S plus 19D, which is not the same as what we had before if we have the offline data, the entire data set. So why is that? Well, the mistake is we're sampling by position, by looking at each coming data set, and we decide if we want to keep it or we want to remove it from the sample, right? So the total number of D queries with and without duplicates is this. This is in your sample, right? This is the number of D queries, and because Tom and Tom, you have 2 queries in the sample, so times 2. Plus, this is your movie. This is also your D query, but only one word got selected into the sample, so this is 2D over 10. Okay. So what was the problem? Why aren't the sample give us similar or exactly the same result as our offline approach? Well, the expected number or the expected value of your sampling approach should have the same value, same result as your offline approach. So, but the mistake here is we are sampling by position. So that means when the search tuple arrives, we are going to flip a coin and retain the sample, the tuples, if the coin shows up as 0. So sampling by position is not ideal. What we can do is we can actually sample by keys or sample by users. For example, when the search tuple arrives, this is a tuple, we can identify a key in the tuple across all tuples. And in this case, we say, all right, user is the key. We will take user as the key. User here in the tuple is the key, hash this word, this user ID or a stream of a username into buckets, 10 over 9. And we're going to retain all tuples for the users in the bucket 0. So this means we are not sampling based on the position, based on when they enter your system. We are sampling your tuples based on content. That means in this case, we are going to keep some tuples for some use. We are going to keep all tuples from some users. Right. So for example, if you have 10,000 users, you take 1/10 of the user, but you look at all their data. You're not going to sample their data anymore. So this is also called sample by user or sample by key. You can sample, the sample is all queries for users that got hashed into a bucket 0. All or none of the queries of a user will be selected so that you will not have a bias. You are not going to have some partial queries from a user. So that the fraction of the unique queries in the sample will be the same as in the data stream as a whole. All right, let's take a 10 minutes break. When we come back, I'm going to continue on this, but if you have question, feel free to post it in the chat.
Hi, Professor.
Yes.
I have a question on page 13. Page 14, actually. I don't understand why Movie and Tom are are different from 13 to 14, because Movie appeared 2 times and Tom also appeared 2 times.
Right. So Movie and Tom, they both appear 2 times in your original data, right?
Yeah.
But in the sample, it could be for a movie, only one of the movie is selected into the sample. The other movie got thrown away. For Tom, both of them got selected into the sample.
Oh, okay.
All right. Makes sense?
Yeah.
Okay. All right. Think about this over the break. All right. 10 minutes and we will be back. Okay, I'm back. Let's continue. All right, so query with sample. Let's look at sample. Solution is very easy, right? Instead of sampling by position, we are now looking at a key. Let's say the key is the user ID. And we say we only sample 1/10 of the user instead of sampling 1/10 of the tuples, regardless who the user was. But the general sampling problem is like this. Let's say you have a stream of tuples with n component. That means your data set or a data point has n dimensions. The key would be a subset of the dimensions or the subset of the components. You have some search stream, the stream that you want to search. This is your sample size, 1/b. It was 1/10 in our example. The sampling strategy is you take the key, you hash the key into some B buckets, and you accept the key if the key value is larger than A, right? In our example, it's 10 buckets in what? Oh, smaller than A, sorry. So example, let's say your tuples has employee ID, department, and salary. Your query is the average range of salary within a department. If you do randomly selected tuples, you're going to mix some salaries from some departments, right? You're going to mix departments together. And the solution is you just take the department as the key and you sample some department and all tuples in this department, right? So if you have 10 departments, you only want 1/10 of the sample. You're going to take one department, and discard all other departments. All right, easy. That's your fixed portion sampling. That means you have a fixed portion that you want to sample. And the second algorithm we are going to talk about for sampling is fixed size sampling. This is also called the reservoir sampling. This is a commonly used algorithm. So the problem with fixed portion sample is the sample size may still grow too big when your data stream comes in, right? Because you say 1/10 of the data stream, but you do not really know the size of the entire data stream. Even 10% could be too large for your memory to store. For example, if you just sample the department ID or user ID, the buckets in the tuples in your bucket 0 could be larger than your memory size, right? Bucket 0 to bucket 10, sorry, bucket 9, because you have 10 buckets. And you take the user ID, you hash them, and everyone who comes into 0, you are going to keep them as your sample. But what if this bucket has too many users and your memory cannot really store this sample? It's too big. The idea is we still want to throw away some queries, but the key is we want to do this consistently. That means we need to be able to remove all or none of the occurrence of a query. But what does it mean? How do we do this? For example, we start with an upper bound of the sample size, say 10%. Okay, we do not know if we have the 10% of the memory 10%, we do not know if we have the memory space to store the 10% of the data that we need, right? Might not enough. So the solution systematically throw away the data set that you don't need or the data sets that's over your memory requirement is you hash your queries into a large number of baskets, right? Remember before we said if you want to have a 1/10 of your queries in a sample, you just have 10 buckets and you keep the first bucket. But if you want to be able to overcome the challenge of having a really large data stream, you can actually use a much larger number of buckets, say 100. So for 100 buckets, if you still want to sample 1/10 of your data, you will put the tuples that hash into bucket 0 to 9, 10 buckets into your sample, right? That's 1/10. When the sample grows too big, all these buckets from 0 to 9 already, all the data points in your buckets 0 to 9 has exceeded the memory you have, then you're going to throw away bucket 9 and so on, right? If your data, your sample grows and grows and grows, outgrows your memory space, you throw away 9, you throw away 8, you throw away 7, and so on. So this way, your sampling rate is not 10% anymore, right? Because you are throwing away data in your sample, but you are systematically sampling your data and put them in the sample. You're systematically selecting your data and put them in the sample, okay? All right, so fixed size sample. Suppose we need to maintain a random sample S of the size exactly as tuples instead of percentage. How do we do this? Well, it's usually a memory size constraint, right? It's easy to know how many tuples we need, and it's difficult to know the percentage because you do not know how many data tuples are going to come, so that the percentage, even 10%, might be too much for your memory size. This is also, well, this is mainly because we do not know the length of the stream in advance. And let's say, suppose at time n, we have seen n items. Each of the item is in the sample S with an equal probability S over n, right? That's easy to understand. So if we think about this problem, let's say your sample size is 2. You only have 2 tuples of memory space to store your sample. And this is your data stream. And the property that we want for specific, for the sampling algorithm is that at n equal to 5, let's say we have looked at the first 5 tuples. Each of the first 5 tuples is included in the sample S with equal probability. Oh, S should be 5. Sorry. You want to have 5 tuples in the sample, right? So when you see the first 5, you're going to store them in your data. At n equal to 7, each of the first 7 tuples from A to C needs to have equal probability for being selected in the sample. An practical solution would be to store all the n tuples, then you select samples, right? That give you the equal probability. But this is impractical because in the first place, you don't have enough space to store all the data points. If you cannot store them, how do you select them? Are we good? I think I might need to. All right, let me do this again. This is your data stream. And we have S equal to 5. In your sample, you can keep 5 tuples. And we want to keep equal probability of selecting a tuple in the stream into the sample, right? A should have the same probability, X should have the same probability, C should have the same probability of being selected into the sample. So how do we do this? If we look at the stream at n equal to 5, it's very easy, right? You have 5 space to store the tuples, so you store everyone. And the probability of being selected into the sample is 1 for everyone, right? Because they're all in the sample. When you have n equal to 7, A, X, C, Y, Z, K, C, you still have 5 space in the sample. And you want to select 5 of them, 5 out of 7 into the sample. and you want the probability to be equal. For example, A should have the same probability as X, as C, as Y, as Z, as K, as C, right? A naive solution that does not work is you're going to store A, X, C, Y, Z, K in your memory, and you randomly pick 5. And the reason why this is not practical is because you just don't have that memory space to store all the data stream, right? So imagine that after you have n equal to 1 million, if we're going to use this naive approach, you're going to store 1 million data points in the memory and pick 5 so that they have equal probability. So this is not going to work because you cannot store all of them. So how do we do this? The algorithm is called reservoir sampling. The algorithm tells us that if you store all the first S element of the stream into your sample, right? We know that in this case, every element has 100% of the probability to be selected into the sample. Suppose now you have seen n-1 element in the data stream, and your nth element arrives. Okay, n is larger than s. Say if s is 5 and your n will be 6 when your number 6 element comes in. In this case, you are going to select this new element with the probability of n or s over n. So given this probability, you are going to keep this n element in the sample, or you are going to remove it. Okay. So you know that if you want to keep this element in the sample, you have to remove one from the sample. So how do you pick the one that you want to remove? If you pick the nth element to be in the sample, then you have to replace one of the s element in the sample, and to pick the one that you want to replace, you just pick one at random. In this case, the algorithm will maintain a sample S with the desired property. That means no matter how long is your data stream, every tuple that you have looked at before has equal probability of being selected into a sample. After n elements, the sample contains each element insofar, and each of the sample with the probability of S over n to be selected into the sample. Okay, so how do we prove this? We can prove this by induction. Assume that after n element, the sample contains each element insofar with the probability S over n. We need to show that after seeing the n plus element, the sample will still maintain the same property. So that means the sample contains each element insofar with a probability n over n plus 1, right? Because now you have seen n plus 1 samples. So what would be our base case? Well, because we want to do induction, you have to have a base case. The base case is when you see n equal to s element. So in this case, the sample S has the desired property because each of this n equal to s element in the sample will have the probability S over S equal to 1, right? Because every element is selected into the sample with 100% probability n equal, let's say n equal to 5, S equal to 5, right? Your sample size is 5 and you have seen 5 tuples so far. So you put everyone into the sample and the probability is S over n, which is 5 over 5, 100%. Inductive hypothesis, after n element, the sample S contains each element insofar with the probability S over n, right? This is our hypothesis. Now we want to prove that when n plus 1 arrives, we are going to keep the same probability. The inductive step, for elements already in S, the probability that the algorithm will still keep it in the S is as follows. All right, so the first one, this one means this new element n plus 1 element is discarded. Right? Remember, this is the probability that we are going to put the new element, the n plus 1 element into the sample. So the complementary probability here tells you that you're going to throw it away. If you're going to throw it away, you are not going to touch your sample. So your sample will stay in the, all the element in your sample will stay in the sample with a probability of what? 100%. Also, you have the probability that your element n plus 1 is not discarded, right? You select it into the sample. You say, I want to keep it. And this is by definition of the algorithm. You have the probability of s divided by n plus 1. Once you do that, you need to replace an element, right? And we said the choices of replacement in the sample is random. So what's the probability of being chosen in the sample for replacement? Is s minus 1. Oh, the probability of still stay in the sample, not being selected in the sample, is s minus 1 over s, because you're going to only replace 1, right? The probability of being selected for replacement is 1 over s, and the complementary is s minus 1 over s. All right, cool. So this is the probability of an element that's already in S will still in S after the n plus 1 element arrives. Okay, two cases. You discard the n plus 1 element, or you retain this n plus 1 element, but you did not select this particular sample for replacement so that it's still in the sample. And if you organize this, it becomes n over n plus 1. Okay. So at time n, your tuples in S were there with a probability S over n. We know this from our hypothesis. When n becomes n plus 1, the time from n to n plus 1, your n plus 1 element arrives. Your tuple stayed in S with the probability n over n plus 1, right? This is what we just derived. So the probability of a tuple is in S at time n plus 1 is its original probability of staying in the sample from time n times the probability of still staying in the sample at time n plus 1, and cancel each other, becomes S over n plus 1, right? Pretty cool. So we proved that after n element, the sample S contain each element seen so far with the probability n over n, S over n. And when n plus 1 arrives, the probability becomes S over n plus 1, right? So every element will have the equal probability. All right, so that's the reservoir sampling approach, and that's all for sampling. The next topic I'm going to talk about is filtering. As specifically, we're going to talk about the Bloom filter. So stream filtering, a few applications here. The first one is a spam filter. A spam filter will check the incoming emails against a large set of known email addresses, say 1 billion, and see if this new incoming email is a spam email, right, based on the email address. Or you have URL filtering when you do web crawling, right? You have a large database with 1 billion or several hundred millions of URL already, and you want to check if the newly discovered URL has already been parsed. And if it's already been parsed, you just throw it away, you skip that URL. So the same scenario is you have a new data comes in, new tuple comes in, and you want to compare this new tuple with a large database to see if this new tuple to see whether or not this new tuple exists in this large database. And we are saying that it's large database, so it takes time to do this comparison to find an answer, and we don't want to do this. We don't need an exact answer. We want to have approximate answer that could be wrong, but we want this to be very, very fast. So how do we do this? That's your Bloom filter. Bloom filter is also a very common, a very popular algorithm. I think some of the mainstream relational database use Bloom filter like Postgres to figure out if you query for an item without running any queries by comparing index and all that computational expensive processes. It will just use a Bloom filter to give you an answer or as a filtering step. So the Bloom filter, formally, it will check if an object O is in a large set S without comparing O with all objects in S explicitly. Okay, either using hash or anything. It does not compare them. The Bloom filter has two properties. First, it does not have false negatives. That means if a Bloom filter says no, it's not in the S set, then your object is definitely not in S. Okay, this is good. But it may have false positives. If Bloom filter says yes, it's in the data set, it is possible that O is not in the data set. Okay, so this is where we said approximate answer. So let's look at how Bloom filter works, and then let's look at the false positive rate. The components in a Bloom filter, the first one is you need to have an array A of m bits. And initially, you're going to set this array with all zeros, right? So m bits from A0 to n minus 1. You are going to have a set of hash functions. Each hash functions will take the object, the input object or tuples string element as the input, and you are going to return a position in the array. Right? You are going to map that input into a position in the array. And you have a set of objects already. Right? Could be 1 billion URLs. So with these three things, now we are going to construct and apply the filter. The construction of the filter is easy. You take each object O in the S, you scan the entire database or archive once, you apply each hash function to O. You can have multiple hash functions. If hj, this hash function of O, returns a position, you just set this bit array at position I as 1. Okay, if it's 0, you just leave it. And during the application, for testing time, you check if a new object S prime is in O, right? This is something you want to know. You hash this object using each hash functions you have. And for some hash function, the return position I has 0 in the array. You will stop and say this O prime new object is not in S. Okay, very simple. But this might not be the easiest way to understand it. So let's look at some examples. Say you have a 11-bit array. Your array has 11 positions. Your stream elements are integers. You have integer script comes in. You have two hash functions. The first one is saying that the odd position bits of the integer from the right mod 11. This will give you a number from 0 to 10, right? And hash function, the hash function number 2 is the even position bits from the right mod 11. This will also give you 0 to 10. Okay, two hash functions. So this is just made up for hash functions. You don't have to use something like this. So let's look at how we construct the filter. Say these are the stream element, these are the hash functions, and these are all the stream elements you already have in the database. And this is your filter. Okay, originally your filter contained all zeros. When you scan your S set, your database, you see a 25, and you start to apply the hash function, so you count the odd and even bit. So in this case, hash function number 1 takes 25 and returns 5. Hash function 2 takes 25 and returns 2. So what does 5 and 2 mean? Well, for your hash function number 1, it will set the position 5 in your filter into 1. So 0, 1, 2, 3, 4, 5, right? See, it converts 0 to 1. Hash function 2 works on the same filter, the same array. It will set the position 2, so 0, 1, 2 into 1. Okay, awesome. That's it. You just continue to do this for all the elements in your database. For example, again, 159 going to hash function number 1 gives you position 7, goes to hash function number 2 gives you position 0. So we are going to set position 0 and 1, 2, 3, 4, 5, 6, 7 as 1. So now you have 4 ones. 585 hash function number 1 gives you a 9, hash function number 2 gives you a 7. So 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. It's already a 1, so we leave it. 8, 9. 9 was a 0, you set it to 1. All right, so that's it for Bloom filter. This, after you do this for every element in your S set in your database, now you have a filters. You have a filter or an array of ones and zeros. Now, how do we use the filter? When the number 118 comes in, the question we want to ask is 118 in our set? Remember, there's no false negatives in Bloom. Okay, so that means if Bloom says no, it's not in your set, it's not in your set. But if Bloom says yes, it's in your set, it could be a false positive. So you take 118, when 118 comes in, you run through hash function 1 and hash function 2. Hash function 1 gives you a 3, hash function 2 gives you a 5. Then you just look at the filter. So position 3, 0, 1, 2, 3 is a 0. All right, so you can actually stop here because it's at 0. That means 118 is not in the set, right? If 118 is already in the set, this position would be set to 1, because when you scan your S set, you see 118, you're going to generate these two positions and you are going to set them to 1. If you have a 0, 118 is not in your S set. Chen Yuan said it's similar to PCY bitmap. Let me think. So for your PCY, you have frequent bucket, right? And the reason why you are in a frequent bucket is, yeah, it's quite similar to the PCY because you can have false positives. All right, so, oh, sorry. We were here. All right, and if we look at 38, is 38 in the set? So you take 38, you run through H1, you run through H2, H1 give you a 2, H2 give you a 5, and you look at the filter. So position 2 gives you a 1, so okay, 38 might be in your set, and 5 also gives you a 1, so 38, the answer will be yes, it's in the set. But 38 is actually not in the set because this 1 and this 1 was set by the number 25, right? So this is a false positive. And whenever we have false positives, we want to understand what are the reasons we have these false positives and what would be the false positive rate based on the setting of your algorithms or based on parameters of your algorithms. And in the case of a Bloom filter, the false positive is the case where X is not in your set S, but identified as in S. So the reason could be for all hash functions. The reason is for all hash functions, your X hashed into one position, right? So this means a collision has happened. So think about this. When we rely on this array to tell us if this new data point is in S, would you have a higher false positive rate when you have a longer array or a shorter array? Okay, the question again, say high false positive rate. What will happen when you have long array or a short array? Okay, Luke is right. When you have a short array. So when you have a short array, let's say what would be the shortest array? Well, that would be 1 bit, right? And your hash function will just hash everybody to that bit and set it to 1. Then when your new data set comes in, it's always hashed into this bucket and it always has a 1. So you will always return, yes, it's in the data set, but it might be wrong. So for all hash functions, X hashes into a 1 position. That will be your hash function X equal to some element in S with a hash function. And this hash function doesn't have to be I, right? It could be this I is hash function number 1 hashed X, because all the hash functions share the same array. This one might give you 2, but hash 1 E give you 3, so there's no collision, great. However, hash function 2 E equal to 2. Hash function 2x equal to 5. Right, in this case, the position 2 has been set by hash function 2 on E, right? So the hash function doesn't have to be the same. So let's look at the false positive rate. We already know that the length of the bit array has an impact for the false positive rate. How about hash functions? Well, the number of hash functions will also have an impact. So in what case will we have a higher false positive rate? More hash functions or less hash functions? Anybody? More. Because when you have more hash functions, it's likely that the probability of a bucket being set to 1 is higher, right? Now you have many more hash functions that would likely to set you to 1. And M is the number of elements that we have inserted into the filter so far. So this is the number of elements in your S. Say your F is the fractions of ones in your bit array after you scan the entire S data set. Your false positive rate is F to the power of K. So this is the probability of saying yes to the question is X in the set, right? Because when your new element comes in, this X comes in, you're going to use a hash function to hash it and see if you have a 1. And your probability of seeing a 1 will be F, right? For the first hash function. For the second hash function, the probability of seeing a 1 is F as well, and F as well, and so on until you have the last F for the last hash function. So if you have K hash function, the probability of saying yes is F K, power of K. This does not mean the answer can be this does not mean the answer cannot be correct. This can be correct, but we are looking for an upper bound for the false positive rate. So we just use the probability of saying yes as the false positive rate. Okay. And we also know that your f is smaller or equal to m times k divided by n, and this is an upper bound. Why is this an upper bound? Because you have n element in the array, and you have m element got inserted. Each of the m element, each element is going to set k at most k positions to 1, right? And if there is no collision, this is the maximum of the maximum numbers of ones that you can set by using all the elements in your S set. And by dividing this number by n, you have the fractions of 1 in your bit array. For example, we're going to look at one example here. For example, let's say your n is 8 billion. You have 8 billion bits in the array. Your m is 1 billion. You have 1 billion object in your set. Your k equal to 1. You only have one hash function. Your false positive rate is estimated to be, well, not false positive rate. The fraction of ones in your array is k times m divided by n, right? So every object set a location to 1, right? So m times k, which is 1, divided by the total number of locations in your array. So that's 1/8. So at most, 1/8 of the bits in the array is 1. And your false positive rate is 1/8 to the power of k, and it's 0.125, right? So this means every time when you have a new x comes in, the probability of saying yes. So your false positive rate is definitely going to be smaller than this or equal to this. All right, so is this good? Well, it's not very good because this upper bound is very loosely defined. So the fraction of ones is the probability that a bit in the array is set to 1 by at least one hash functions. And the total number of hashes is k times m. If we want to adjust our estimation, let's first consider throwing d darts on t targets, right? If you think about m and a hash function is throwing a dot every time you're trying to hit a target in your array, now you have t targets and you have d darts. So what's the probability p of given a target hit by at least one dart? Oh, give me 1 minute. Okay, I'm back. So what's the probability p of given a target hit by at least one dart? The probability of a target not hit by a dart is 1 minus 1/t, right? A dart. And the probability of being hit by a dart is 1/t, right? Because you have t target, you can only hit one target by a dart. And not hit will be the complementary probability, so 1 minus 1/t. The probability of a target not hit by all darts, and because you have d darts, so that's 1 minus 1/t power of to the power of d. And since 1 minus 1/t to the power of t is this, and this can be e to the power of -1 for large t. Why? Well, because of this. Your Euler number is 1 plus 1/n to the power of n when your n is very large, right? So if you compare this with this is just a rewritten of this. right? You cannot directly use this because you have 1 over t and you have t here. And here you have 1 over n, and you have a plus sign, and here you have a minus sign. So if we move the minus sign to here, and minus t, right, make this 2 the same sign, just like here, and take a minus 1 here because you have a minus t here. Originally it was a t. And replace this item with your Euler number, it becomes e to the power of minus 1 over e for large t. Cool. So if we know this, then this, right, this is your probability. And because you want to have a t here, so it will becomes t times d over t becomes this, right? Because we replace the core with the Euler number. So it's e to the power of minus d over t. And the probability of given a target hit by at least one dart is 1 minus e over 1 minus e to the power of minus d over t. Cool. All right, so how do we use this? Well, based on our example, the fractions of ones is the probability that a bit in an array is set to 1 by at least one hash function, and we know it's this. So what is our d? Our d is the number, the d is the number of darts, right? In this case, it's k times m. And how many targets do we have? That's the number of bits. So it's this. Once we know this, your false positive rate, instead of having this rough estimate, now we have f equal to this. So the false positive rate is our new estimate, and this is multiple hash functions hit the same bit. All right, that's it for today. And on Monday, we are going to look at some examples, and I'm going to summarize this and to have your quiz. Thank you, everybody. We are going to have our office hour today. If you are not going to come to the office hour, you can leave now. See you next week. If you are going to the office hour, I will see you in 2 minutes. Thank you, everyone.
Thank you.
Hello, I'm back. Any questions?
Yes, Professor. I have some quick questions. And can I share my screen?
Sure.
Okay. So my question is about the building filter. So my first question is that how to get the 5 for each one? Is that a makeup number or how to calculate this one?
Oh, you don't have to. No, it's actually on the previous slides using the beat and generate a number.
Yeah, like for the first one is 5 because the 5 is the first number. So how to get 7?
You take the even beat, odd beat, and you put them together and generate a 7.
So 1, 1, 1. Oh, okay, okay.
Yeah, it's not important. It's
Okay, okay.
really not important.
Okay. So and then after we do this and we got a like filter like this, and so then we can check whether 118 is in the set, right?
Right.
So and this is just like true negative, and if we check 38 and although it meets the filter, it does not in the set. So 38 is the false positive.
Correct.
Okay, and so based on this formula, so with the more hash functions we got, the less false positive rate we can get.
The more what?
The more hash functions we have, the less false positive we can get. The less rate
No,
we can get.
more hash function, you're going to have
because f is less than 1, so all f times together. Is that correct?
Right, that's correct.
Okay, got it. Thank you very much. So,
sure.
So the quiz will include both the streaming part and the cluster you taught before.
Yes.
Okay.
That's correct.
Hi, Professor. I have a questions about the clustering, the BFR algorithm.
Sure.
And there was a part, I know that in the algorithm, we need to, there's one step is to find out the DS, the discard set, the compress set, and the RS set. So I'm still a little bit confused about how we actually in the algorithm, how we find what are the points that are considered, close together. Like for example, using the looking at the DS set.
So for DS set, in your first round, you only have centroid, right?
Yeah.
So you can use a Euclidean distance and use the distance threshold. You say if you're close, then you belong to the DS set. In the second round, once you have the structure of the cluster, you can start to use the extent of the cluster to help you.
What do you mean by the extent of the cluster?
Sure, let me show you.
Yeah.
Or maybe I'll just show you the description of the assignment. Give me 1 second. Let me find it.
Okay, thank you.
Okay, here. This is not the final version, but it's close. So this shows you the implementation details for the BFR algorithm. Your first step is going to load. Can you see my screen?
Yeah. Yes.
Okay. Your first step is to
Yes.
load some data points, right? And this says what from one file is one chunk. Then you run the k-means algorithm on the data points, and then you have some centroid, right? So say for the implementation, you can apply k-means on a small set in this one file and generate a centroid. So now you have centroid.
Yeah.
But you still have lots of data points because you are only using a subset.
Yeah. Oh,
So-
I'm sorry. When you say all these data points, this data points belongs to the data file that we haven't read in, right? The
you already
points.
read in.
We already did. Okay.
Right. Say you only have 3 parts. You read in the first part.
Yeah.
Right. And the first part contains 1 billion data points. And you don't want to do clustering on 1 billion points because you still do not have that memory space to run it. Although you can load it, you might not have the memory space to run it.
Oh, okay.
So what you can do is you take some subset of the 1 billion, say you take 1 million, and you generate 3 centers.
Okay.
And these 3 centers also give you some cluster structure, right? From the 1 million data points. So there are multiple approaches. You can start to assign the remaining 1 billion minus 1 million points to the clusters. The first approach is you can just compare the distance between the points to the cluster center and use a threshold. You can say if you're close to the center, I'm going to add you to this cluster. Then it becomes the DS set. Or you can use Mahalanobis distance like we discussed in class. Right, Mahalanobis distance will consider the variation in each dimension, and it will use square root of d. Now, use the standard deviation to help you set a threshold. So still have a threshold, but at least you have some way that takes into account the variation within the cluster. So that's the cluster extent. That's how I call it, the cluster extent, like this. Right, so once you can do that, now you assign many of the points into the DS, then you throw them away, you just summarize the clusters. Okay, then for all other data points, you can do a clustering again with a large K to identify your CS, and you keep going. So there are many different ways to implement the BFR algorithm. In your homework assignment, we're going to tell you one way to do it. Because as you can see, I already told you many different ways, right? You can use Euclidean distance from a data point to the center. You can consider the structure of the cluster and use Mahalanobis distance. So many different ways. Is that clear?
Yeah. Okay. Thank you. And just one thing, just want to make sure, because if we are using Mahalanobis distance, I remember there's a way that there's one step that required us to normalize the data point, right? So in this case, how should we consider that? So
it's not normalizing your point. It's in the definition of Mahalanobis distance. You have to take a point and subtract the mean and divide it by your standard deviation of that dimension. So it's standardization. And you don't have to do any pre-processing because that step is within your calculation of Mahalanobis distance.
Oh, okay. Got you. Because I was just thinking that if we have to consider that, then we already have to do the calculation with all the data point. And then that seems a little bit too complicated. I mean, too complex in terms of efficiency.
Right, not for the 1 billion data point. You only do that for each cluster.
Okay, got it.
Because you want to know the distance between this point, right, this point here to this cluster. And in this case, you have 2 dimensions, right? So to calculate Mahalanobis distance, you want to consider the variation in Y dimension and in the X dimension. And how do you know this? Based on the data points within this cluster,
Mhm.
right? So
Okay.
it's not 1 billion points.
Yeah, that makes much more sense. And we have to do it with each of the clusters, right?
Right, right.
Yeah. Okay. Sounds good. Thank you.
And if you wanted to run fast, you can parallelize everything, right? Because all these steps are independent.
Oh, yeah, right. That makes sense. Thank you.
Cool. Thank you. All right. Any more questions?
Hi, Professor. I just
Oh,
want to continue his question. In the first
sure.
round, we need to find the DS. Do we need to set a threshold? Is a user-defined threshold?
Yeah, it's user defined.
Oh, okay. Thank. And another question is, for the homeworks 4, we need to find the number of cluster before calculating the modularity. We need to count the age with the highest betweenness. What about if 2 ages with the same betweenness? The two highest betweenness.
Oh,
Do we
you
need to
remove
cut
all of
both
them.
of them?
Yeah, you remove all of them.
Okay, thank you.
Sure. All right. Anybody? No more questions? That's it? All right. Thank you, guys. I will see you next week. Have a good weekend. Work on your assignments. Read your textbook.
Thank
Bye.
you. Bye.